Hello, everyone. My name is Amanda Haller with Audio Precision and Axiometric Solutions brand, and today we are featuring audio testing in smart devices. Today we have Eric Schulteis as our presenter from Axiometric Solutions. Before we begin, I wanted to cover a few housekeeping items. A copy of today's slide deck is available through the handout section on your screen, along with other various related handouts. If you have any questions during the webinar, you can submit them through the questions section on your screen, as all audience participants will be muted during the presentation. We will try to answer these questions during the webcast, but if a fuller answer is needed or we run out of time, you will be followed up with after the webinar via email. Without further ado, I would like to pass it over to Eric to get us started.
Thank you very much. Hello, and welcome to the Audio Precision and GRASS Sound and Vibration Smart Device Audio Testing webinar. My name is Eric Schulteis, and I'll be presenting the following slides to you today. Here's what we'll cover in today's webinar. I'll make a short introduction to our company's products and services. I'll talk about open and closed loop audio measurements and how these apply to testing smart devices. We'll look at basic audio tests, some of the measurements you'll need to make. I'll discuss procedures for testing playback-only devices as well as recording-only devices. And then next, we'll look at a test system component list you may want to consider. And I'll leave some time for questions and answers at the end. I've been working at Audio Precision for 20 years, where I work on the global tech support team. I support Audio Precision and GRASS products alongside my colleagues here in Beaverton, London, and Copenhagen. When I'm not supporting our customers and products, I enjoy playing guitar, practicing yoga, and outdoor activities like cycling, hiking, and kayaking. If you have questions or need assistance with the topic we're covering here today or other issues, please reach out to us by email at techsupport@ap.com or support@grassacoustics.com. It doesn't really matter which address you use. They'll both be seen by our team. Audio Precision was founded in 1984 by 4 engineers, Bruce Hofer, Rich Cabot, Bob Metzler, and Bob Wright, who met each other while working at Tektronix. For almost 40 years, we've been the recognized leader in audio test and measurement solutions. We design, manufacture, and service our products here in Beaverton, Oregon, USA. While many customers are still using the original System 1, we have progressed over the years, adding performance, features, and capability, while streamlining the user experience. GRASS Sound and Vibration was founded in 1994 by Gunnar Rasmussen. GRASS is recognized in the industry for innovation, groundbreaking designs, and a dedication to customized customer solutions. All GRASS products are made in Holte, Denmark. GRASS products are available for a wide range of electroacoustic testing applications, including measurement microphones, ear simulators, head and torso simulators, test fixtures, as well as calibration solutions. IMC Test and Measurement, located in Berlin, is the third company under the Axiometric Solutions name. Together as Axiometric Solutions, we provide test and measurement solutions for many markets, applications, and customers around the world. Now we'll jump into this by taking a look at closed loop audio test. As the name implies, the loop or signal path is closed. That is to say, the audio stimulus generator, the device under test or DUT, and the audio signal analyzer are all working together at the same time in harmony. The generator creates a pure tone, usually, but not always, sine waves, sending the signal to the DUT's input, while the DUT's output feeds the signal back to the audio analyzer, which will compare the received signal to the original generated signal and then calculate and post the results. Here are some examples of devices which can be tested in a closed loop configuration. Basically, any device that passes an audio signal from its input to its output in real time. When making an open loop audio measurement, the signal path or loop is open, meaning the generator and the analyzer are not working together in concert. They are separated from each other. This type of signal path configuration is necessary when the device under test is not able to pass the stimulus signal through its input to its output in real time. In many cases, the DUT may not have physical inputs at all. The input to this type of device could be a file in the cloud, on a network, on an SD card or a disk, or an analog recording on vinyl. Some devices do have inputs. However, the input may be difficult or impractical to access, so open loop testing is the preferred technique. DUTs which require open loop testing fall into three main categories: playback only devices, record reproduction devices, and broadcast or transmit devices. To test playback only devices, the stimulus signal must be placed onto and then played from the device, or streamed into the device and played from its output into the audio analyzer. This is a two-step process where step one is creating the stimulus signal and moving it to the device or the network. And step two is playing the stimulus signal from the device or streaming it to the device while analyzing its output. Here we see some examples of record reproduce devices. These devices include recording devices, smartphones, tablets. This category of DUTs has two signal paths, record and reproduce, each requiring an open loop configuration and a two-step process for testing. To test the record signal path, we first play the stimulus signal from the APX generator into the DUT while recording it to the DUT's file format and media. Next, we move the recorded file to the test system host PC and use file analysis in APX 500 software to analyze the recorded file. To test the reproduce signal path, we follow step one, just as described above, and then play back the recorded file from the DUT to the analyzer to be analyzed in real time. Here's the procedure outline for an open loop test of a playback-only device. Step 1 is to configure the generator. Step 2, we generate the stimulus wave file. 3, encode the file for the DUT or the network if necessary. Then we upload the stimulus file to the DUT or the network. Next, we start the analyzer acquisition. Step 6 is to play or stream the stimulus file from or through the DUT. And finally, the analyzer acquires the signal and makes the analysis. Here we see an outline for the record-only device in greater detail. The procedure here is as follows. Step 1 is to configure the generator for the desired stimulus signal. Step 2, we configure the recorded device and start recording. Step 3, we generate the signal. Step 4, stop the recording once the signal has been recorded. Step 5, we transfer the recorded file from the DUT to the host PC. Step 6 is to decode the file if required. And finally, step 7, we analyze the file with APX 500 software. Of course, most smart audio devices have speakers and microphones, which add to the complexity a bit. An electroacoustic open loop measurement might add step 2 above, equalizing the speaker or mouth simulator to produce a flat response or leveled acoustic output. And we're also adding step 8, windowing out reflections from the impulse of a chirp measurement if the measurement is taking place without an anechoic chamber. Smart speakers have two signal paths, the voice command path and the streaming path. The voice command path is a record-only path, and the streaming path is a playback-only path. Now that we've seen smart device signal paths from the outside, let's have a look inside the smart device. This block diagram shows various circuits or components within the device, which can each be tested for quality. Most of these components can be isolated and tested in closed loop configurations, although optional digital input-output modules may be required in the APX analyzer to support the necessary connections. More on this in a few slides. Many audio measurements are made using sine waves to stimulate the DUT. We generate a pure sine wave, which is played or transferred to the DUT. The DUT will play or pass the sine wave back to the analyzer, where it's analyzed for any changes from the original signal. Frequency response is probably the most telling measurement result. We can use stepped frequency sweep, continuous sweep, multitone, and transfer function measurements in closed loop or open loop configurations to show us the response as well as other results. The stepped frequency sweep measurement uses a sine wave stimulus signal that's moved across a range of frequencies in a series of steps or points. Stepped frequency sweep provides a sweep table editor where you can set step points and durations, as well as create a wave file of the stimulus signal for open loop use. Distortion, phase, and synad results are also provided in this classic measurement technique. Continuous sweep is a chirp-based measurement. Using a brief Farina log swept sine or chirp stimulus that moves continuously across a specified range of frequencies. The DUT output is acquired by the analyzer and is mathematically deconvolved to provide a number of results. The continuous sweep measurement has a save generator file feature for open loop testing, and like stepped sweep, provides response and additional results. The major difference between these two measurements is the speed of operation. Stepped sweeps can run for 30 seconds or more, while continuous sweeps are generally completed in less than 1 second. While stepped sweep measurements are historically standardized, the log sweep sine or chirp measurement has some significant benefits. It's much faster. It provides quasi-anechoic electroacoustic measurements plus rub and buzz results. In a closed loop test, the generator and the analyzer work together, informing each other of starting a measurement, moving to the next measurement step, and when the measurement is completed. When making open loop sweep measurements, we use a pilot tone just before the stimulus signal to trigger the start of the measurement. The pilot tone is usually a 1 kilohertz signal. Here's a view of the chirp stimulus. You can see the pilot tone on the left and the chirp signal on the right. Here we see the stimulus waveform for a 350 milliseconds long sweep from 50 hertz to 8 kilohertz with a pilot tone and the wake word inserted before the chirp signal. The analyzer triggers on the pilot tone and uses the pilot tone frequency to correct for the slight sample clock difference between the DUT and the analyzer. In this case, the wake word and the pilot tone are not included in the analysis of the frequency response. The APX 500 acoustic response measurement is a chirp-based measurement with time windowing to gate out reflections from the result. If you don't have an anechoic chamber for making electroacoustic measurements, this will help. Acoustic response measurements can be made in closed loop or open loop configurations. The APX 500 multi-tone measurement, as the name implies, uses multiple sine waves together. This signal is more like program material or music. Smart audio devices employ codecs which reduce audio data rates for streaming. Some of these codecs tend to mask sine wave signals, and as such, we must use a measurement requiring a stimulus signal other than sine waves. In this spectrum display, we can see each of the separate tones in the multi-tone signal. This example uses 31 tones with third octave spacing. The multi-tone signal definition enables the analyzer to trigger on the multi-tone signal itself. Multi-tone measurement does not require a pilot tone to trigger in open loop configurations. Transfer function provides the difference between two audio signals by comparing the complex spectra of the two signals. This feature, which uses FFT analysis on the two signals, is also called dual FFT. One of the most powerful aspects of this technique is that the stimulus signal can be tailored to suit the device under test or the testing environment, as long as the signal is broadband with sufficient energy across the spectrum of interest. Transfer function is an excellent choice for testing the input path of a smart speaker because a speech or speech-like signal can be used as the stimulus, virtually ensuring that the signal will be acquired and processed unaltered by any noise-canceling algorithms or codecs. Transfer function analysis can also be used for the output signal path of a smart speaker using music or noise as the stimulus. To avoid reflections, an anechoic chamber should be used when making electroacoustic measurements, unless you're using the acoustic response measurement with time windowing to gate out the reflections. Next, we'll look at the various components and options for the test system. The APX517B is an excellent match for testing many smart audio devices as it's set up out of the box for electroacoustic measurements. It has a 35-watt power amplifier, a stereo headphone amplifier, 2 microphone inputs with CCP and phantom power options, and a single slot for an optional digital I/O module. It's pictured here with the Bluetooth Duo digital I/O. These are the optional digital I/O modules available for APX analyzers. Up to 4 of these modules can be fit into an APX 52X, 58X, or 555 analyzer. One option module at a time can be fit into the APX 517B. One or more of these optional digital I/O modules may be necessary to test various components, circuits, or signal paths within a smart audio device. The GRASS 46AE half-inch CCP free field measurement microphone is a great workhorse reference mic for making acoustic measurements on smart speakers. It will interface directly with the APX 517 or any other APX analyzer using one of the 12 series power supplies or the APX 1701 transducer interface. The 46AE conforms with IEC standards. The EQ40PM miniature production line microphone is the first microphone to incorporate EQ-set technology. This removes all of the traditional hassles associated with installing, setting up, and replacing microphones in a production line setting. EQ-set microphones all have flat response curves and fixed sensitivity. Sensitivity variation between individual microphones varies less than 0.2 dB from nominal sensitivity. The flat response is less than 0.5 dB up to 10 kilohertz, another huge improvement over traditional production line microphones, plus or minus 3 dB across the full frequency range. The GRASS 44AB passive mouth simulator connects directly to the APX 517B also. This is used for testing microphones in smart speakers and speaking wake words and command words to the DUT. Jigs are included for calibration according to CCITT P51 and IEEE 269.661 standards. The Model 44AA is similar, but also includes an internal amplifier with 10 dB of gain. The GRASS AL0030 production line acoustic test chamber will provide approximately 25 dB of separation for making electroacoustic measurements on a noisy production floor setting. It is built from medium density fiberboard lined with acoustic damping material. A large opening at the back of the chamber allows easy access to the chamber for configuring the test setup. The chamber has shock and vibration absorbing feet that prevent vibration from the outside from influencing measurement results. On the software side, you'll need APX 500 measurement software, which comes with all APX analyzers as standard. APX 500 measurement software is the most advanced audio measurement interface available. Complex procedures that include user prompts, limits, calls to external applications can all be created directly in the user interface. This software controls the APX hardware in manual and automated applications. APX 500 can also be automated via the APX API using Visual Basic.NET, C#, MATLAB, LabVIEW, or Python. While you can use APX measurement software to generate and save stimulus waveforms, this APX 500 waveform generator utility also does the same for mini stimulus signals. The utility is a small standalone application, and it's a free download at ap.com. Another handy tool I recommend is Audacity. This DAW, or Digital Audio Workstation software, is free of charge and open source. It will run on PCs, Macs, and Linux. This is a great solution for building and editing stimulus wave files. Here are some additional sources of information pertaining to smart device audio testing, which may be helpful. You can download these documents from the handouts area here in the webinar. You'll also find these and additional resources on the Audio Precision and GRASS websites. This brings us to the end of this presentation. I would like to thank you all for attending and remind you of the next webinar in this series on June 28th, when the topic will be headphone testing. I would also like to thank Amanda and Teresa for helping to put this all together. So we do have some time here. If there are any questions, we can open it up for that now. Okay, I see a question here. Will you record this section? I believe this is being recorded, and I think it will be available for those who've attended. Another question here is, does the pilot tone need to be the same level as the stimulus signal? No, it does not. It should be fairly close. You wouldn't want the pilot tone and the stimulus signal to be 30 dB apart from each other. But yeah, generally you'd want to keep them pretty close, and you can control that from the software when you generate your files. Another question here we have, can the 517B option modules be changed while the analyzer is working on a production line? Unfortunately, no. To change the option module, you would have to send the analyzer to us. We would make the change, and then the instrument would need a calibration after that. Okay, we have another one here. How does the test measurement handle clock wander of the DUT? Okay, so we have frequency error correction, which will use the pilot tone as a known frequency to autocorrect. And if you're working with a digital input signal, jitter can be handled to a point, depending upon how much wander there is. Can you please confirm the next session date again and topic? The next session date is June 28, and the topic will be headphone testing. Is it possible to use AP hardware to test surround sound capabilities of a DUT? Yes, it is. The APX 585 analyzer has 8 inputs and will analyze 8 channels simultaneously. We also offer the 586, which has 16 input channels. So yes, we can handle surround sound inputs. What calibration is required when amp modules are changed, and can this be done in the field? That kind of is similar to the previous question. So yes, if an digital I/O option module must be changed, then the instrument must be calibrated once that change is done. So this is not a process that's handled in the field. It has to come through an authorized service center for that swap of the module and the following calibration. What measurements can be done using the test chamber? So the test chamber is designed to make any electroacoustic measurement when you're dealing with microphones and/or speakers. And you get about 25 dB of separation from the outside world with that. And because of the size of the chamber, you are somewhat limited to the low frequencies that you'll be able to work with. Okay, is it possible to measure crosstalk on an open loop source like a CD player? Yes, it is. We have crosstalk signals, which will work in an open loop signal path. What is the contact for purchase of GRASS accessory items, couplers, and preamps? Okay, so I would need to know where you're located. This is coming from Jonathan. Jonathan, if you send us an email, you can reach me at techsupport@ap.com and give me your location, and I can connect you with the contact information for that. Let's see if we have anything else. Here's one. Why do I always hear a clicking sound from inside the APX analyzer? So the clicking sound that you hear are relays. Most likely it is the input ranging relays that are clicking. If you have an open microphone on the analyzer and perhaps the door to the chamber is open, or you're on a test floor out in the open, and the input range to the analyzer will be changing based on what the microphone is actually being exposed to, and that will fluctuate. And there's no harm in that, other than, you know, relays do have a life cycle and you don't want to needlessly waste those cycles. So the easy fix for that is to lock the range or disable auto range, and you can do that in the advanced settings tab of the measurement. So it will stop the relays from wandering or searching for a range. Does the AP software include any perceptual audio evaluation metrics, PESC, etc.? Yes, we do offer PESC, Polka, as well as STI, and these options are available for audio precision analyzers. And if you're interested in those, we can connect you up with a demo with your sales engineer. We do have that available. Okay, let's see, here's one that says, the AP often disconnects from the computer. Is there a workaround to prevent this? So there are several things that you can do to prevent this. One of them would be to not use any kind of USB hub in your connection, to keep your connections as clean and simple as possible. Another thing that you might consider is what other items you have running on the PC at the same time. This might be a situation, if you're experiencing this, that would most easily be dealt with in a troubleshooting session here with myself or one of my colleagues. So I would suggest that you send an email to techsupport@ap.com, and we can set a meeting with you to troubleshoot if it can't be done over email. So there are several steps that we would want to follow to have you look at some things on your system to get to the bottom of what's causing that. Okay. If the DUT becomes defective during test, there is a high spike going, and there's a high spike going into the analyzer. Is there any possible damage to the analyzer? Okay, good question. So as I talked about earlier with the relay clicking sound, the auto range circuit in the analyzer will kick in. Even if you have locked it down, it will kick into a higher range if it sees a spike on the input level. So as long as the spike does not exceed the maximum input level specification, which varies depending upon your analyzer. However, you can look at the front panel of the analyzer right there on the inputs, and it will tell you what the maximum voltage that it will handle is. So it does have protection built in within reason, but for most audio signals, you're not going to damage the analyzer. Okay, well, I think that's all the questions that we had. So if there aren't any other questions, I think at this time, I'm going to hand it back to Amanda. And thank you all once again for participating today.
Perfect. Thank you, Eric, for that excellent presentation. And thank you to our audience for your participation today and your excellent questions. An on-demand version of today's presentation will be sent to the email that you registered with. Also, be sure to register for the upcoming webinar, Testing of Headphones and Headsets, on June 28th. That will be included in the follow-up email. To the questions that we were not able to answer today, we will follow up via email within the next few days. We hope you have a great rest of your day, and we look forward to next time.